Hi everyone, my name is Xijun Wang, a PhD student at University of Maryland, College Park. I'm going to present our work SCSC, Spatial Cross-Scale Convolution Module to strengthen both CNNs and transformers. How can we strengthen both CNNs and transformers? Here, first, we present a high-capacity and effective convolution module SCSC, which can dynamically combine a large range of receptive fields in one layer to enhance the presentation ability. Second, architectures applied with SCSC can obtain better performance with fewer computational cost and parameters. Furthermore, SCSC is a general module and can be applied to strengthen both CNNs and transformers. Third, SCSC module can power the classical neural networks, example, ResNet 50, to achieve comparable performance with strong transformers, example, SWIN. Large receptive fields, sparse connections, weight sharing, and dynamic weight have been considered keys to designing effective base models. Based on those rules, we build our module SCSC. Our SCSC can capture microscopic and macroscopic feature representation synchronously without intensive computational cost. As shown in the figure, for SCSC, different from the mainstream CNN small kernel size or the transformer's global receptive field, we design an intermediate expression for the receptive field and spatial modeling ability by using a wide range of kernel sizes from 3 by 3 to 13 by 13. Depthwise convolution is applied for its efficiency. Small kernels, example, 3 by 3, have advantage in modeling low-level and detailed information as shown in the upper red path in the figure. Large kernels, example, 13 by 13, can handle the semantic dependence in a large receptive field as shown in the lower green path in the figure. Therefore, keeping both of them can obtain diverse spatial representations. Furthermore, we design an efficient spatial embed module to aggregate the different spatial representation features, which can capably integrate different levels of information. As a result, in our proposed SCSC, we can acquire different receptive fields in one layer, share weight in both spatial-wise and channel-wise, exploit depth-wise convolution to hold the sparse connectivity property, and apply the spatial embed module to bring dynamic connection across the channel dimension. For clear illustration, we split SCSC into 4 steps: channel reduction, spatial cross-scale encoder, spatial combination, and channel recover. Channel reduction to reduce the computational cost. Spatial cross-scale encoder offers the large range of receptive fields in one layer. Spatial embed module dynamically fuses multi-scale features at each spatial position, i.e., pixel level. Finally, channel recover will recover the channel dimension. To verify the effectiveness of SCSC, we evaluate the effectiveness of our proposed SCSC module by embedding it into the classical CNN backbones, ResNet 50, Mobile FaceNet and FaceResNet, and state-of-the-art SWIN transformer, CONVNet respectively. We conduct experiments for SCSC-based architectures on ImageNet, MS1MV2, COCO 2017 and ADE 20K in terms of image classification, face recognition, object detection, and segmentation. For image classification, we take classical ResNet 50 and state-of-the-art SWIN transformer as the backbone to evaluate SCSC by replacing their original components respectively. As can be seen, for ResNet SCSC v1 and ResNet SCSC v2, we use much less computational cost and parameters to obtain competitive results. For ResNet SCSC v3, with comparable model complexity, we successfully make the performance of a classical CNN architecture, ResNet, match the transformer's performance. For SWIN transformer, with our SCSC module, it achieves a higher accuracy with 1 gigabits, 22%. Flops fewer computational cost. These results show that SCSC-based architectures not only have a considerable improvement, but also saving computational cost and parameters, demonstrating the effectiveness of our method. We also evaluate our SCSC on face recognition. Given that Mobile FaceNet is already an efficient network, Mobile FaceNet SCSC still outperforms the baseline by 1.1% gain even with fewer flops and parameters. FaceResNet SCSC surpasses FaceResNet by a large margin of 2.7% accuracy with 68% fewer computational cost and 79% fewer parameters, further indicating the superiority of our proposed SCSC. For object detection, we compare SWIN SCSC and ResNet SCSC with standard CONVNets and previous transformer networks with mask-R CNN. Our ResNet SCSC architecture achieves 5% improvement over baseline ResNet 50. Compared with strong baseline SWIN Tiny, ResNet SCSC improves 1.3% box AP and 1.1% mask AP over SwinTiny. Swin SCSC achieves better performance even with 23G flops, fewer computational cost and 6M fewer parameters, illustrating that SCSC also works on downstream tasks. For semantic segmentation, compared with SwinTiny, our ResNet SCSC achieves 1.3 MIOU higher than SwinTiny with slightly larger model size and computation cost. For ablation study, larger kernels results in better accuracy, but when the kernel size exceeds 11 by 11, accuracy begins to decline. Our results demonstrate that both excessively small and excessively large kernel sizes are suboptimal. Thank you for your listening. Please feel free to contact us if you have any questions.